Hello, everyone. Today I will talk about how we can use computer vision and transfer learning for identify the diseased bird species. First, let's quickly understand what is the. This approach is actually very important for now, for us to detecting outbreaks of the HPAI at early stage. Firstly, let's quickly understand what is the HPAI. The HPAI, in general, we call HPAI as a bird flu or H5N1, but H5N1 is one of the most dangerous strain of HPAI, and it causes the high death rate in birds and even some of the mammals species. The bird flu isn't just threat to the wildlife. Currently, it's also risk to our economics and the public health. For example, if it costs the billions of dollars loss if outbreaks in country, also it causes high fatality rate if they transmit to the human. So the best way to handle it is to stop before it outbreaks. Let's quickly go over the project background. You can see this is, as you can see, this is the slide, the screenshot from the current HPAI reporting system from MPI website. It requires the reporter to actually provide information such as the dead bird species or the precise location. It's which is kind of impossible in the real life because we are not actually the bird expert, or we don't really have the professional GPS in our hand. We can provide the precise location. So this kind of system is not friendly for most of our users, and which may lead to delay in the identified or responding to the potential bird flu cases. So let's talk about our project goals. The project is, sorry. So the project is to develop a model and deploy on the mobile device to classify the dead bird species and also report their location accurately. So for the user side, for the normal people, for the user side, it will help, the application will help us quickly report the suspect cases. For the authority side, it will help the authority quickly identify the dead bird species, also with the accurately locations. So the project has three main steps. The first one is the data collection and integration, followed by the modeling approach. And the last one, step is comparing the model performance. So let's go through the first one, the data pre-processing. As you may know, for the computer vision models, it mainly based on the image data set. So at the beginning, we actually collect 1,700 images from the open source. And then after EDA, we found there are three major issues in the data set. The first one is data imbalance. For example, like we have most of the, we can find most, like a lot of images from the most common birds species, but you can't really find some like rare species. So that's lead to the data imbalance. And the third one is the quantity of the images. You can see from this slide, they are for example, like that one, the half of the body buried in the sand. Another one, the dead body, the bird dead body is highly tangled with grass, which is made very hard to classify. They are actually the birds, right? So another one is the species complexities. For example, we actually have like, in our data set, we have like 16 of the subspecies of petrel in our data set, which also make very hard to classification due to the limited data. So before we use the data for build our models, we actually need to do some data pre-processing. So we applied three methods. The first two is first one is down dampening and up dampening. Next one is up dampening. The reason we're doing this is actually we actually try to balance the data across the species. And the last one is like we actually, because we don't have that much data, so we have to recategorize those 109 bird subspecies into like 27 higher class species due to the, like I said, due to the limitation of the data. So now we move to the model approach part. In this slide, I'd like to show you, show you why the pre-trained model doesn't work. As you may be aware, like there are actually hundreds or maybe thousands of computer vision models exist out there already. So instead we actually build our own model from scratch. We can just use it, right? So we test many of the different architecture of the computer vision model, and we actually found like the model actually doesn't quite work well with the dead bird species, data set. That's the example of the model's performance. You can see the test loss is very high, and the model is not convergent, and it shows a clear pattern of the overfitting. So after some analysis, we actually found that's because the future is different. The source future and is so different with huge difference with the targeted futures. In the computer vision lingo, that's called domain shift problems, issues, such as you can say such as the lighting background or even the dead bird body is so different with the live bird body. So we can't use the pre-trained model. We have to find our own way to solve this problem. So now that's the main part of our project. So we actually, to solve this problem, domain shifter problem, so we actually designed a pipeline framework that combines the feature extraction and SVM classifier to create more effective models. Here's how it works. First, we actually test the different pre-trained models, such as CNN-based or the vision transform-based models, and the layers for features extraction, as you can see here. And then we use that extracted feature as input data for the downstream classifier, training the downstream classifier. Then we actually, so to further improve the model's accuracy, we applied a PCA or normalization method to do it, and then we compiled. Then finally we compiled the result to find the best combination of the method. So that's the two best performance we've actually found. One is the first one is the efficient net B7. Another one is vision transformer. The both model achieved the similar accuracy on the test data set. But there is some difference, such as the VIG model. They acting faster at the feature extraction stage, but efficient net is actually performing faster than when training the downstream classifier. And both models do have like a struggle with the specific birds classes, as you can see from here. And this insight actually help us to better understand the strengths and the limitation of this two approach. So let's go with the findings. The first finding is the future extraction layer matters. We actually found the future extraction, the choice of the layer is significantly affect the downstream, the accuracy of the downstream classifier. The second is the batch size impact. The larger we found like a large batch size actually improved the accuracy of the downstream model. And the third is hyperparameter tending sensitive to the models, only sensitive, the hyperparameter tending only sensitive to the CNN-based model, not VIT models. And however, both models, they do still have domain shift issue problems. So they still have it. We are not actually solve it like 100%. This not actually matched like source domain didn't fully match to the target domains. And for the computation time, overall we actually found the CNN-based like model is actually take less computation time compared to the VIT models. So the last we found after like hundreds of tests, we found the best combination of this hybrid model is efficient at B7 plus PCA plus SVM, which achieving 85% of the test rate. So in conclusion, we actually implement a pipeline framework that integrates the transfer learning and traditional machine learning technique to address the domain shift issues in the limited data set. What's the great about these models? It actually takes the strengths of both approach. First is deep learning. As we know, a deep learning model is very good at future extraction. And for the SVM, as a traditional machine learning classifier, it works very well with the high-dimensional features. So the hybrid model actually achieves much better test accuracy compared to we just use the pre-trained model alone. So it also helps us mitigating the domain shift issues during the future extraction. So there are three major advantages of the hybrid model. The first one is the efficiency use of the data. As you know, we only have like 1,000 usable dead bird images. Also, instead of like other computer vision model, they normally trained on the larger amount of the data set, like ImageNet or COCO. The second is the less training time. Compared to we train a computer vision model, we normally, if you want to get a very high accuracy of the model, you probably normally train over 50 epochs, which take lots of time. The third one is like we actually mitigating the domain shift problem instead, but not solve 100% solve it. So the future, so this project is like we don't actually go further on to solve the domain shift problem. So future research we can focus on it to add more like advanced domain adaptation method to further actually improve the accuracy of the model. And for the last slide, I want to quickly show you the demo of the model deployed on the server. so by sound. You can find the most the hot spot of the bird observation spot. And you can try yourself if you scan the QR code on your mobile device. And that's my presentation. Thanks very much.
I guess I have a lot of questions. That was really great. Thank you so much. My main question was the data set. You said you got the dead birds data set. Can you talk more about where that data set came from?
It's mostly from the online open source. So it's mainly from the iNaturalist. So the images uploaded by the users. So yeah.
Could that wait until welcome function? Yeah. Thank you. Thank you so much, Zhuo. Thank you.
Thank you.